How does PyLabRobot know what a plate looks like? This is the first of a short series of introductory videos in which we'll explain how you can generate multi-well plate definitions. The aim of this first video is to show you how you can quickly generate a basic definition for a well plate. More advanced well plate features such as automated computing of liquid height and volume inside wells, liquid level following during aspirations and dispensations, or how you can automate the generation of these well plate definitions using PyLabRobot enabled machine functions will be covered in a later video. So let's dive straight into the code. New well plate definitions are generated most efficiently by taking the definition of an existing plate and modifying the parameters for your specific well plate. Here we can see the definition for a 96 well plate manufactured by a company called Ascenta. Note that a definition could be generated by simply writing plate, opening parentheses, adding the parameters, and then closing the parentheses. However, when writing a new automated protocol, which is sometimes confusingly called a method by classic automation engineers, we want to give a specific plate definition an easily rememberable and informative name. This is why in PyLabRobot, or in short PLR, we generate a function with that name and let it return the parameterized plate object that represents our physical plate for us. When writing a new Python-based automated protocol, we can then easily generate a new plate instance by calling this function. Additionally, defining plates through functions like this means we can use the PLR convention for resource naming we see over here. First, the name of the original manufacturer of the well plate, in this case Ascenta, in the Fortitude Framestar product line. Sometimes plates are resold and their name is changed. It is important to search for the original manufacturer for naming a new definition to avoid redundant definitions. Next, we see a number that represents the number of wells that the plate holds. In this case, we learn that the plate contains 96 wells. Then we read that the resource is a type of well plate, with each well having a maximum utility volume of 200 microliter, and that each well has a V-shaped bottom. Finally, in the docstrings of a well plate function, we can find further information that is useful for knowing what well plate is being defined. At the very minimum, the docstring must contain the original manufacturer catalog number, but ideally the docstring contains additional information regarding the material properties of the well plate and the automation standards that it adheres to. Now let's see how to take measurements of the physical plate to fill the parameters for a new definition. In this scene, we can see two plate holders next to each other. We just placed the 96 well plate on the plate holder on the left. The first thing we must do is measure the X, Y, and Z dimensions of the plate. However, most plates have a narrower top than bottom, and to figure out whether to measure the top or the bottom dimensions, we have to keep in mind how PLR models resources such as well plates. In PyLabRobot, well plates, like all resources, are modeled as cuboids, or in other words, boxes. That means to PLR, this 96 well plate appears as a cyan-colored cuboid. Every resource has an origin, which is defined as the front left bottom of the physical geometry, highlighted here as a cyan-colored point light. First, notice that the dimensions we need are the plate's bottom dimensions. After measuring these, we add them to the plate function on the right. Next, we deal with the lid information. Because we're only creating a basic definition here, the plate has no lid, so we set the lid attribute to none. The model attribute in the plate function is simply the name of the plate function itself. This makes it easy to find specific well plates in the directory during an automated protocol. Now that we've got the basic information of the plate, we have to define the positions and dimensions of the wells that this plate houses. This is done with the plate's ordered items attribute. Ordered items expects a dictionary of wells and their relative positions in relationship to the plate. However, creating the dictionary of an array of wells is so common that PLR has a handy helper function to generate it called createOrderedItems2D. Now let's go through what measurements we have to give createOrderedItems2D. For this purpose, let's generate a cross-section cut of the physical plate at row H. But let's keep the digital representation of the plate object as a transparent cyan cuboid, so we don't lose track of what the plate looks like to PLR. Here we see the definition of what a well looks like to PLR as a yellow-colored cuboid with its well origin highlighted as a yellow-colored point light. Defining what dimension should be included in the definition of a well has been surprisingly difficult. Multiple questions have come up. For example, should the well definition include the walls to its side that generate the cavity of a well? After some testing, we decided to define a well as only the empty cavity in the x and y dimensions. That means the well definition does not include the walls in the x and y dimensions. The reason is quite simple. We can easily measure the well cavity's diameter with a caliper, but the walls can often not be measured at all. However, in the set dimension, the well definition does include the well wall for reasons that we'll get into in a bit. Now that we have the basic definition of the first well, createOrderedItems2D needs to know how far away this first well is located in relationship to its parent's origin. In other words, how far away is the well's yellow origin to the plate's cyan origin. This information is given in the attributes dx and dy for the x and y dimensions respectively. Note that we do not measure from the well center, which stands in contrast to some other research management systems that you might have encountered in the past. Instead, always ensure that you measure the well's front left bottom origin to the plate's front left bottom origin. Here we can see that the dz measurement has to be taken slightly differently to the dx and dy measurements. Since the well definition includes the well wall in the set dimension, the dz measurements is simply the distance between the bottom of the outside of the well to the set plane of the plate origin. However, there is one crucial measurement still missing: the thickness of the well wall in the set dimension, which is called material set thickness in PyLabRobot. This is needed because together the values dz plus material set thickness define where a tip has to go when we ask the machine to aspirate or dispense from a well bottom. Without this information, the tip is likely to crash into the bottom of a well. Finally, a well plate has, of course, not just one well, so we have to tell PyLabRobot how far away different wells are from each other in the x and y dimensions via the item dx and item dy attributes. This plate has, of course, 12 wells in the x and 8 wells in the y dimension. The cross-section of each well is a circle and the bottom is V-shaped. Other well bottom types include flat bottoms and U-shaped bottoms. With this, we have finished the basic definition of a new well plate in PyLabRobot. But before leaving, let's have a quick look at the importance of defining material set thickness correctly. First, in this scene, we can see two plate holders. One plate holder has a flat surface and the other has a central elevation. In PyLabRobot, we call the central elevation a pedestal. In a separate video, we will go into the details of how to define plate holders and their pedestals. Now let's move the well plate to a plate holder with a tall pedestal as shown here on the right. Let's remove the tall clamps of the plate holder so we can more easily see the interaction between the plate, the well's material set thickness, and the plate holder's pedestal. Here we can see that the plate is actually submerged beneath the top surface of the plate holder by exactly the value dz. This means a good research management system automatically computes whether a plate's dset value is smaller than the height of the plate holder's pedestal and automatically adjusts the origin of the plate to its real position. The inside bottom of the wells is then just above the surface of the pedestal by exactly the material set thickness. Giving your well plate definition all this information means that PyLabRobot can accurately model these interactions, and you do not have to constantly use specialized offsets that essentially make your automated protocol into a rigid house of cards, which will fall apart as soon as you change something as simple as a plate holder. We will go into further details of the dynamic and autonomous deck management this enables in future videos. For further information, please visit the PyLabRobot Documentation and the PyLabRobot Forum linked in the description. Happy automation, everyone!